I hope to talk today about learning for a target population by combining information from multiple sources. And so this problem comes up in many guises. I believe last week the previous seminar was on a very related topic. I'll tend to emphasize maybe the causal and study design aspects of the problem, but we'll see how much we can go through. So I should say this is joint work, some of it ongoing with a lot of different people. In particular, I think I want to mention Sarah Robertson and Guanbo Wang, who are postdocs. They're the younger, more junior people on the list. And then Yuhan, I think you all know Yuhan. She's abandoning us for another university. But it's been a pleasure working with her and continuing to work with her. And then anything I say is my own opinion, not the funders or any other organization. So I want to talk about a broad class of epidemiological problems. What makes them epidemiological is that the parameters of interest are defined in terms of a target population. And so those could be treatment effects, they could be associational parameters, they could be descriptive parameters, but somehow we want to know about a causal effect or an association in a target population of interest, perhaps one where a decision is to be made, like when approving a drug for use or when deciding whether to cover a drug for the population of insured individuals. And so what happens in many of these cases is that the relevant information comes from multiple sources. For example, you have multiple trials about a topic, or you have more than one surveys that have studied related populations to the one you're interested in. So the task in those cases becomes to somehow synthesize the evidence that is available across different sources and then somehow transport or extrapolate or extend inferences from all these diverse sources to the target population of interest to the investigators. And so whenever this topic comes up, people think, rightly so, about meta-analysis. And so the best thing I can say about meta-analysis right now is that it's very popular. You can see this is not cumulative, by the way. This is new meta-analysis publications per year. And then I think it's a remarkable thing what happened in 2020 and then 2021 and 2022. This goes up to 2022 because it's the last complete year. There is an explosion even faster than it used to be, and many people have hypothesized that's because postdocs and PhD students, junior people were sequestered in their homes, so they couldn't really do field research, but they could still read and synthesize papers. And so if that's true, maybe this will be the first time it starts going back down. And the other thing I need to say is I did some of these. I mean, a teeny fraction, of course, of the thousands and thousands. But if I say anything that sounds critical, it is mostly self-criticism. So why do I think there is a problem with relying on conventional pooled analysis or meta-analysis for the kinds of target population problems I introduced before? It's hard to summarize hundreds of methods, publications on meta-analysis, but I'll try to do it in 3 bullets. So all these methods, what they do is some of them provide, in some sense, an optimal summary of the existing data. Perhaps this is the view espoused by Dr. Richard Pito, one of the pioneers of meta-analysis. And I think he writes and he says in talks, including talks here, that the goal is to summarize the existing data as efficiently as possible, and then all generalizations beyond the data are informal. So somehow you think what you found gives you a sense about at least the direction of effect in the population you're really interested in making decisions, or patients for whom you're making maybe clinical decisions. And so this is good, but to me it seems a little historical. It's like I'm summarizing things, but I'm not allowed to do any formal extrapolation beyond the existing data. The second strategy is to make a somewhat strong assumption that the marginal, usually for randomized trials, the marginal treatment effect or the marginal association is common across studies, exactly the same. The true parameter is exactly the same. And that seems hard to believe when for most problems we accept heterogeneity, at least on some scale, to be quite pervasive. Then the third and probably most popular now strategy is to model the distribution of study effects. Maybe some people will write the population of studies, but the idea is to hypothesize an infinite distribution of effects or studies that could be conducted, and then somehow the data you have are sampled from the population, and you summarize it to learn about the parameters not of a human population, but a study population. And so that seems a little fanciful. I don't really know what is the population of all trials about a particular treatment, but it also seems unsatisfactory because it's fundamentally switching the question to a question about human population or maybe its members to a question about studies. It has its uses, but the interpretation most people try to get out of it, I think, is not completely tenable with the assumptions it makes. And so I think a common problem across all these approaches is that the results inherently don't pertain to any well-defined target population, even if all the studies examined the exact same treatments and had the same follow-up protocols, because the population underlying its study is different, and they may be different with respect to important modifiers of the treatment effect or the risk or the association of interest. And so, since there is no clear causal interpretation that can be given here, except as a strange weighted average. I call the weighted average strange because all these methods have in common that in some sense, the averaging takes into account the precision of the study. Informally, you can think of it as taking into account the sample size, for example. And so if you think about what drives the sample size of a given study, let's say a clinical trial, if we are honest, if we look in our hearts, we admit it is practicalities of doing the research, in particular how much funding there was available, because if you had more funding, you would ask a harder question and you would recruit a bigger sample. In other words, the sample in many cases is determined by the practicalities of conducting the research as opposed to the population for which the research is to be informative. And so the weights are strange because they reflect the availability of resources and coincidences that affect the conduct of the studies instead of representing the real underlying epidemiology, if you will, of the problem. And I can't do justice to all the approaches. There's many ingenious ideas for combining data. Some of them go under multi-parameter evidence synthesis that at least honestly grapples with the difficulties of combining information when there is various kinds of biases, including non-representativeness. But the final methods end up being subject to these limitations. In particular, for multi-parameter evidence synthesis, almost always there is some assumed distribution of effects. So I claim the standard methods are not completely satisfactory for the goal. Instead, what appears to be a better idea, a better way of approaching these problems of combining information is to take maybe a principled approach, some kind of framework, if you will, that starts from the research question and goes down using tools tailored, of course, to the specific problem. And so here I have a convenient list. I'll try to highlight some of the steps in the slides that follow, but just to give you a sense of all of the steps. And they are not sequential necessarily. Many of these steps take place in parallel. There is many opportunities for iterating, but it's useful to have them in some kind of order, at least a first pass order. So you start with your research question, and I'll give a causal example in the next slide. And then you somehow have a study design and sampling framework, meaning somehow you get observations or person time into a data set. And in the problems we're going to study, you cannot make do with a single data set. You have lots of them that have relationships between them that you'll have to somehow model. But just putting these together gives you some kind of data structure, and then you look at that data structure, you combine with that with the knowledge of how the data is collected and your own understanding of the causal problem for causal examples, data generating mechanism, if you want a more general term. And then that causal model allows you to express the answer to your research question in terms of a causal estimate. And again, I'm narrowing it down now to causality. And so you have the formalization of the answer to your research question, and you have a causal model. You somehow extract from that, perhaps your causal model is expressed as a beautiful causal diagram. You extract from that identifiability conditions. And this will allow you in step 8 to express your causal estimate as a statistical estimate, something that can be obtained from data. In between the identifiability conditions and identification, which is the process of writing the causal estimate as equal to some kind of statistical estimate, there is the interesting step that when combining multiple data sources, your assumptions, your causal model, or maybe your causal model and your sampling model impose restrictions on the distribution of the observed data. This is something that hasn't escaped notice for decades. For example, in conventional meta-analysis, if you assume a common effect, it has to be that the estimates of the studies within sampling variability agree between them. And so your belief that there is a common effect has a testable implication for the average results. Here also a somewhat more intricate case that follows from the causal model. Suppose then that the assumptions are credible and you have your identification result, then you proceed with a statistical task of estimating that statistical quantity and maybe doing inference for it. And of course, many of the assumptions, as I will show in the specific example of causal meta-analysis, are very strong. Some may say even fanciful. And so there's always room for some kind of sensitivity or bias analysis, or perhaps triangulation with other techniques, different data, different assumptions. And then you end up with something that is definitely more complex than conventional meta-analysis. So there's a challenge of communicating these results to decision makers or to the public and convincing them that they are useful for the purpose they have. And so I won't speak a lot about step 10 and 11 just because of time constraints, but 11 in particular appears to be a non-technical human factor challenge that I think will become more pressing as we get more complicated data structures and perhaps more model-based inference. So to highlight the elements of the framework in particular from 1 through 9, I'm going to use causal interpretable meta-analysis, basically our proposal for how to use something that resembles meta-analysis, but maybe with a hope of getting a clear causal answer. Okay. So let me start with a research question. Let's say you're asking something like, I have 2 treatments, I want to know what is their comparative effectiveness, and these treatments have been combined in 2 or more randomized trials. And I want to know what would happen were these treatments to be applied in a new target population, the one I'm interested in. And in that population, perhaps further experimentation is not feasible. In particular, any data I obtain from the target population, if they include the treatments of interest or alternative treatments for the same indication, may be subject to confounding. I just don't have control over how the treatment is assigned and used outside of the trials. So to go through the steps of the framework, I'll have to introduce a little notation, and this will require a strong dose of the work with me principle. Why? Because I will study the simplest case. There will be no missing data, there will be no non-adherence, so everyone gets the assigned treatment in the trials and in the target where they to be assigned it. That's not because these are not interesting or common complications. In fact, life has delivered many disappointments when we think we have a perfect data set for some illustration of these methods, and then you really need to make many tweaks and improvements because of practical difficulties. But to introduce the concepts and have something that we can go through in something like 30 minutes, work with me and allow me to use that simplest case. Okay, so my notation is going to be for the trials, I'll gather all of them in a collection as calligraphic, and there's a finite number of trials in my telling. You can think of this as a fixed number of trials, and they go 1 through M. Now I'm going to use capital italic numbers for random variables. So the S italic, capital S italic, when it takes values in the set S calligraphic, is going to just be some specific trial 1, trial 2, trial M. And then I'm going to have covariates X, all of them at baseline. Again, work with me principle. I'm doing the simplest case. There is no non-adherence. The treatment is a point treatment. And so the baseline covariates perhaps are enough. Treatment will be capital A, outcome will be Y. And then in addition to having X, A, and Y data from each of the trials, I'm going to assume that you can characterize your target population, which is a non-randomized population, in terms of some kind of collection of data for covariates, at least. And then I'm going to use the convention that that sample, if you will, the target population itself will be denoted by capital S 0. So 0 is the target, 1 through M are the trials. And so again, work with me principle. You were warned, you'll have to work with me. The trials examine the same set of treatments. In fact, in my examples, I'll often talk about a binary treatment because it's the simplest case. And so every trial compared the same active treatment, let's say against the same placebo or against the same comparator. It is quite easy to generalize the simple case to multiple treatments, including the case where some of the treatments have not been studied in some of the trials. So that's the case of network meta-analysis or indirect comparison meta-analysis. The price to pay for doing that more general case is just extra notation, because one has to keep track of the sets of studies in the meta-analysis that actually studied some of the treatments. And so this S calligraphic, for example, may need to be indexed by the pairs of trials being compared. And so it gets a little more tricky to follow that notation, and I don't think you gain much more conceptual clarity for the set of assumptions I'm going to use. So I'll just do the binary case. Now, all that sounds a little theoretical, so I like to look at pictures like this. And so this is a schematic of the data structure created by appending the data from the 1 through M trials, as well as the sample from the target population. And so S0 is the target population. These are the covariates, and I told you I don't need, and it turns out the assumptions allow me not to need treatment and outcome data from the target population. That doesn't mean the people there have to be completely untreated or that their outcome cannot be measured. It's just that under the assumptions I'll state, that piece of the data is not necessary. This can be viewed as a benefit, for example, when the treatments are not available widely. For example, if my treatment in the trials down here is a new experimental treatment not on the market, we expect that there is no one receiving that treatment, and there may be variation among other treatments up here in the S0. Another thing that will happen is because I won't necessarily need treatment and outcome data from the target, again, because I'll be making certain assumptions, a benefit is I don't need to assume anything about the structure of confounding in the S0. And so it may be that there is confounding, but I won't need to assume it away. The other benefit is sometimes trials have really interesting outcomes that simply are unavailable in sources of information for target populations. So for example, a committee adjudicated major adverse cardiovascular event is something that just doesn't happen in routinely collected data or survey data or most observational cohort data, but it is quite routine in large, definitive, randomized trials. And so that may be something that's unavailable. And of course, many lab measurements or exotic imaging outcomes are just not available widely in representative target population samples. If A and Y are available, if A and Y information is available from S0, nothing is lost. You get some opportunities to make different sets of assumptions and perhaps triangulate them against the ones I'll be using here. But again, I'm studying the basic case, and I'm happy to talk about the complications. And these down here are the trials, and they're all appended together. They go 1 through M. They have covariates treatments here drawn to be binary and outcome measured everywhere. For convenience, I create this new random variable that basically is 0 when S is 0 and is 1 when S is anything except 0. So you can think of this R as just keeping track of whether I have a trial in observation, a trial-based derived observation, or a target population derived observation. And so R0 means it's equivalent to S0. R1 just means one of the 1 through M values of a trial. And then this just writes down the data. I'll have a different, potentially different sample size from its trial. And for the trials, I'll get to see X, S equal to the trial they come from, R1 automatically when S is in the collection, A and Y. And for the target population, I'll have just X. And then whenever I know it's the target population, S is 0, and that gives me immediately R is 0. And then just to keep track in some of the formulas, this composite data set that combines the trial and the target population data has some kind of sample size that's determined by summing up the sample sizes of the individual trials plus the S0 sample. Now, I am cutting corners here in stating a causal model completely in counterfactual terms. We could, of course, have a graphical causal model, some structural causal model. I'm just not going to write that out. But in my heart, I want Tyler to know I believe in such a model that can be expressed by a DAG. It's just that it, again, would take a lot of time to introduce that machinery. And so in my model, there will be these well-defined counterfactual outcomes. So they'll mean the outcome under intervention, possibly contrary to fact, to assign treatment little a, which belongs in the set of treatments studied in the trials. And then, since there is perfect adherence, this can also be thought as the counterfactuals for receiving the treatment, in my little simplified example. And so my parameter of interest is going to be an average treatment effect in the target population. That targeting, you can see, happens because I am conditioning the expectation of the difference of potential outcomes on R equals 0, which is the same as S equals 0, which is the target population. And then just by linearity, I really have to worry about the individual means, the counterfactual potential outcome, if you like, means, under each of the treatments studied in the trials. Now, the reason to focus on the means is not only that they make everything a little easier in presentation, but also because they're of inherent scientific interest. My experience with clinical collaborators has been that, of course, everyone is interested in treatment effects, but everyone wants to also have a sense of what would be the baseline risk or the risk under the baseline control treatment. And so being able to estimate the means is useful for many practical problems. But it does simplify the math a little bit, that we'll only have to worry about one of the means. And so I'll make 6 total assumptions, and the first 3, I feel for people in the school, are pretty believable. You'll give them to me, I think, if I just go through them quickly. So the first one is some kind of consistency of potential outcomes, which of course has to be argued case by case. But it says if a unit in my population receives treatment little a, their counterfactual outcome will be precisely equal to their observed outcome. This can fail, for example, when there is multiple versions of treatment or interference, but I'm just, again, work with me principle, not going to deal with these harder cases, to focus on the concepts of combining evidence. Then there will be some exchangeability over the treatment variable in its trial. This is given to me by randomization. It is supported by design, and so it says that the potential outcomes are independent of treatment, possibly given the covariates, and conditional on each of the trials. And we expect that to happen, for example, if the collection of trials is a collection of simple, marginally randomized trials. In fact, in that case, this assumption is weaker than the one given to you by the physical act of randomizing individuals to treatments. Informally, this just says there is no confounding for the effect of A on Y in the trials, which again we kind of accept because of randomization. And the third assumption is also given to us by design. It says that if I think of each of the treatments being randomized in the trials, and I think of each trial, then for every covariate that can that has positive density in these trials, the probability of receiving the treatment given the covariates in its trial is positive. And so again, that makes sense because the coin flip I'm doing to randomize will never give probability 0 to the treatments I want to compare within my trial. And since we studied a case where all the trials have the same treatments, this is acceptable. Again, you can see if we wanted to generalize to some treatments not being evaluated in some of the trials, then that positivity condition would only need to hold for the treatments actually randomized in those trials. And so that comes with extra cost in terms of notation, so we won't pursue it. Now the next 3 assumptions are the ones that are a little more exciting for this problem. The first one, and I think the first one can only be done justice if we were explicitly writing out our structural causal model. Now I'm going to state it as an algebraic requirement. It's something that says if an individual receives treatment little a, then for every trial, the counterfactual defined in terms of putting that person in this trial and giving them treatment little a, by the way, I say giving them treatment little a because we said perfect adherence, that's equal to just giving the treatment. And so this essentially says that the effect of the treatment I'm looking at is context independent in this particular sense. You can also think of this, if you like instrumental variable work, this should look like an exclusion restriction type assumption that essentially says there are no arrows in your underlying causal diagram that I haven't written from S into Y that don't go through A, such that when you intervene on the A, you don't need to know the S. I'm actually making S an instrument for being assigned the treatment, but nothing else. And so in practical terms, assumption 4 precludes, for example, Hawthorne effects. It says that knowing you're in a trial doesn't affect your outcome as long as I know what is the treatment you're getting in that trial. It also precludes effects of trial participation on the outcome that are not just measurement effects. So for instance, in many clinical trials, the frequency with which you attend clinic visits is increased compared to routine practice. So let's say I am asked to return to clinic every month, and the treatment I'm being randomized to is some antithrombotic for preventing heart attacks. If every time I go to the clinic, which happens at higher frequency in a trial than outside the trial, I'm also reminded to diet, exercise, stop smoking, all these actions that are parts of the trial not happening necessarily with the same intensity in regular practice may conceivably affect, let's say, my cardiovascular outcomes. So those would be cases where the participation itself, by exposing me to that protocolized interaction with a healthcare team, affects my outcome, not through the treatments I'm being assigned. It turns out without this assumption, without assumption 4, we can still get workable identification results, but they are identification results not for just receiving the randomized treatment, but also for adopting all outcome relevant aspects of the trial protocol. And so in some sense, these are less interesting because we don't always have the ability to pinpoint which aspects of the trial are affecting the outcomes other than trial participation. I'll just say this assumption is one where I found statistical people with statistical backgrounds more resistant to it, and I found clinical people much more willing to believe and see its necessity. And I think that comes from a long tradition of thinking that in randomized trials, many things are happening to the people, not because of the kinds of characteristics they have, but because the trial has its own process which may affect the outcome. In fact, in oncology, effects of trial participation on the outcome, not through randomized treatments, have been explicitly described as effects of hypothetical interventions to randomize people and have been used to argue for the ethical case for trial participation in oncology. That is, the people in the control group experience benefits more than usual care because of the trial process, unrelated to the treatments being randomized themselves. So it's an interesting aside. Assumption 5 is the one that does hard work. It's an assumption that says the potential outcomes are not just independent of treatment, which we had on the previous slide, but now they're independent of participation in a particular study given the covariates. In other words, I'm saying my X information is so rich that it is enough to render the potential outcomes under each of the treatments I'm interested in, independent of participation in a particular study, including being in the target population. This is strong. It can be weakened in multiple ways. One of the ways I'm going to try to get to on the slides, in the paper linked here, we give a lot more ways in which the assumptions can be weakened, including assumption 5. And so again, work with me principle. I can only do one set of assumptions in 15 minutes remaining, but we did have some ideas, and perhaps this is an area of active work, including for our group, to see how much weaker a condition like condition 5 can be made. The obvious way, of course, is to assume it only for the difference between treatments, a claim essentially that there is no residual effect modification when you adjust on X. So that's an obvious weakening which we pursue in the paper, but I won't talk more about. And then the sixth assumption is also strong and also not justified purely by design. So I have to know something about the problem I'm studying, but it says for the covariates that can have positive density in my target population, that's the R0, I have positive probability of those covariates being found in each of the trials I'm combining together. And this one is obviously very strong, and I'll also weaken that one on the slides in a second. Okay. Now, what did I mean when I said there's implications for the observed data? This, I think, is the cleanest, shortest illustration I could get. You have the potential outcomes independent of X, of S given X, which is an assumption. It turns out if that is true, the potential outcomes are also independent as an implication of that assumption they're independent of the indicator for any trial versus the target population. So this says the potential outcomes are not only independent of S, but when they're independent of S given X, they're independent of R given X. It's built in the assumptions. Another thing that you get, and this is just algebraic properties that I don't really think we should spend too much time on, you get an independence of the potential outcomes from S, not just given X, but restricting your attention to the set of trials and given the treatment that was randomized in the trials. So this one is getting interesting because I can just think of that assumption which is implied, I can think of this independence which is implied by my assumptions for a specific value of A equal little a. In which case, by consistency, I get an independence of the observed outcome from the cohort, from the trial, from the population, given X, R1, and A equal little a. And since this last independence does not involve the counterfactuals, it is testable. If you want a simple way of testing it, you run a regression of Y on X in R1 and A equal little a. And in that regression, you put S, and then you run the same regression without S, and you do a likelihood ratio test for the two regressions. I'm not saying this is the optimal way to test the assumption. Maybe you want to do it in a way that is much more data adaptive, doesn't require parametric models. It is possible to do a non-parametric version of this test. But just to connect it with things that I feel everyone knows, this is just saying if I put the S in my regression of Y on X, and that regression is run only in the R1 A equal little a, my test should not reject. I shouldn't need to have S to improve my fit. And so I'll admit that this is as far as I'll go with this independence. It's good to have it as an implication of the assumptions. It can be viewed as a falsification test. I will say explicitly, don't test it and only do the analysis if it fails to reject. I will say don't test it and keep testing it until you find a set of X's that don't reject this independence. I'm not advocating for any of these things. In fact, these things will lead to very poor coverage of the estimators. We and others are working on ideas for how to allow the testing to happen, and then if the test doesn't reject, do valid inference. But I don't have much to say about that today, maybe in a couple of years. Okay, so in terms of identification, what happens with my assumptions and my target of interest here is that the assumptions allow me to express it as a statistical quantity. And this statistical quantity should look reasonably familiar if you like the treatment effects literature, the causal effects literature. Because my assumptions allow me to say that the potential outcome mean under treatment little a in the target population can be written as a nested expectation, maybe in this school we say a Z formula, and that Z formula has the expectation of the observed outcome given the covariates in the collection of trials, all of them together, among the people who got treatment little a, and then it marginalizes, averages that regression over the covariate distribution of the R0s. So we did use a lot of causal machinery to convert our target of inference to some statistical quantity that is essentially a standardization task. And it turns out this has an equivalent expression in terms of weighting. It's not really inverse probability weighting because it involves the odds of being in R0, not the probability, not just the probability, but the odds. And also it involves a term for the probability of treatment. I've noticed many people really don't like this term. It's fine. This term is, you can think of it as correcting for small potential imbalances in your trial, or you can think of it as being a more general result that allows you to use this formula when the studies are not trials but observational cohorts in which X is sufficient to adjust for confounding. I like to think about trials because that seems to be the main use case for meta-analysis, but all the results are written in a way that they can address the confounding case as long as the treatment is a point treatment and baseline covariates are enough to address confounding. Okay, this is the promised, let me skip. This is the promised weakening of the assumptions to handle the more interesting cases where you don't make as strong assumptions. So in the meta-analysis literature, one thing you often hear is that the real reason we do meta-analysis is that each study is different, and so combining them together somehow allows us to learn about populations that are broader than the population underlying each study individually. And so there is a formalization of that notion on this slide, and it says, what if instead of thinking of the implications of the assumptions on the previous slide, I take them as primitive? So now I'm not starting by saying the potential outcomes are independent of S given X. I'm just saying they're independent of the indicator for any trial versus some trial. And my positivity condition does not require a positive probability for being in each trial given the covariates, but it requires positive probability for being in any of the trials, in the aggregate collection represented by the trials. And so if you do take these as primitive assumptions, you can see perhaps that the identification result remains exactly the same. But we haven't required each study to be representative of the target population on its own. Instead, we just want the collection of them to somehow be representative. Now, I personally think these are unlikely to be true if the stronger ones are not true, but it is a mathematical fact that these are weaker than the ones on the previous slide. So once we get here, we have identification, and so the remaining tasks are statistical, and I won't present too many details, and this is the last step of the framework I'll cover in detail. But the point is now once we have a statistical quantity, we can use the machinery of statistics, maybe semi-parametrics for my use cases, and try to find a good estimator for this quantity. This is a data quantity, so it's the subject of statistics. And it turns out that can be done, and we worked out the details, and everything is in the paper I linked earlier. I won't go through the pain of the steps for getting to this expression, but I do think there is profit in glancing at it and seeing how it connects with things we may know. It definitely has a term that involves the expectation of the outcome among the people who receive treatment little a in the trials. So you can think of this as an outcome regression fit in the collection of trials, maybe separately by arm. And this term appears here, and it also appears in a way where it somehow centers the observed outcomes. And this centered term, which has mean zero if your model for the outcome is correct, is being weighted by something that involves, perhaps not unexpectedly given the identification results, the odds of participation in the trial, the inverse odds of participation in the trial, times the inverse of the probability of receiving the treatment you actually received. So this should be eerily similar to results from the average treatment effect on the treated literature, where we are averaging among the R0 group and viewing it as a treatment. In fact, all my results can be recast by thinking that there's not just the A treatment, but there is two treatments, the participate in the trial treatment and the receive treatment, little a treatment, and they're jointly applied. Both of them are unconfounded. That's given by the assumptions. And then and one of them happens to not affect the outcome except through the other treatment, in which case you get my identification results and you get this expression for estimation. And again, I don't want to go into details about technicalities, but the reason to have both weighting and outcome regression together is that you get certain model and rate double robustness properties. So you can get the outcome regression wrong, but if you get the probability models right, this estimator will, in large samples, converge to the true value. Or vice versa, you can get the probability models both wrong. This one is hard to get wrong with trials. Usually it's just a half for everyone. But this one can be definitely misspecified, the model for this one, in which case if you can get the outcome regression in the trials approximately correct, you'll get the consistent estimator in large samples. And there's, again, more technical results, but by combining these two models in the same expression, you also get the ability to use data adaptive, methods that converge at the true model at a rate slower than the parametric one. For example, some machine learning methods, you get to use them for these quantities and still do valid inference. And of course, these statements are not very satisfying technically. The details, we think we have all of them in the papers. Okay. Now, at this point, I could show you a bunch of simulations that no one wants to see. And plus, I designed the simulations. There were no surprises. Like in computer science, the method proposed is the method winning, always. So I won't show you those. Instead, I'll show an empirical illustration. And if time allows, I want to touch very briefly on some issues that have to do with source selection and observation sampling, and maybe discuss some potential paths for future work in that space. So my empirical illustration is going to repurpose a trial data set. So we took a multi-center trial. That trial is called HALT-C, and it had 10 centers. The reason to use a trial is that in each of the centers, randomization is working for us. So we have a way of estimating a treatment effect that, in principle, is unbiased in each of the centers. And so our task is going to be to hold out one center and see if we can, from the other 9 centers, learn the treatment effect in the held out center. And what we did is we took the largest center, and we also did it by taking the largest center that was very different from the others when analyzed on its own, and the results were similar. So we took the largest center and we said we're going to pretend this is our S0. And then we're going to use trials centers, if you want, 1 through 9 as trials. And we're going to use them to learn about the S0 center, the held out center. So that gives us roughly 200 patients for S0 and about 770 patients for the trials. And these have different sample size, as you would expect. Every center recruits a different number of people. And what we did is, first of all, we said, let's see what happens if we try to transport each individual center, each individual trial, to the S0, and let's see what happens when we combine them using the methods I presented just now. And then, just briefly, we had a lot of covariates. This is a trial that collected very rich baseline data, so that's another reason to work with this. We modeled the outcomes separately by treatment group. We tend to do this to allow for no restrictions on effect modification. And then we use linear regression because the outcome is going to be platelet count at 9 months for drugs that we generally expect reduce the platelet count. And so this is what the results look like. The gray solid line is the result of analyzing the target center alone. The dashed lines, the dashed gray lines, the vertical ones, are the 95% confidence interval for an analysis of the target center, the S0 alone. The squares, the white squares, are the completely unadjusted, as reported in the trial, analysis of each center separately. This is conventional in multi-center studies, is to do an analysis of each center, and you can see some centers appear to be quite different from others. The black squares are the center by center, study by study, transported results to the target center. The reason these are much narrower than the unadjusted analysis is because we are using the outcome information in each of the centers, and so we can improve the efficiency of the trial. So in some sense, the improvement in precision that you see between the white squares and the black squares is an improvement in precision that is always available to trialists, and they just decide to leave that money on the table, so to speak. But you can see once you do that adjustment, the results still have quite a bit of variation. In particular, some centers have non-overlapping confidence intervals between them, and the point estimates are quite dispersed. But then you use the method of pooling the centers under the assumptions that I stated and with the method that we looked at before, and you get this diamond down here. And so you can see the benefit is the result is very similar to the target center, even though obtaining this number involves no treatment and no outcome from the target center. So in some sense, we're extrapolating to that target center. And so the point estimates are very close. The scale here, we're talking about something like 2,000 platelets, I think, maybe 3,000 platelets. And the confidence interval is fully nested within the confidence interval of the target center and includes the point estimate of that center. So in my book, success. Of course, this was a nicely chosen example where the data was very rich, and we looked at the short-term outcome, and the assumptions we're making appear to be approximately reasonable here. I'll also say, incidentally, at the end, we did test the independence, and we failed to reject with a p-value that was very, very large, like 0.7. Okay, now, can I go for 5 more minutes or no? Okay. So, no simulations, but I do want to talk about some practical things that we've come across and where I think there is room for more work. So the first one is kind of philosophy. Maybe the art of epidemiology is in the first one. But in my telling, everything was kind of given. You knew which studies to combine, and the only thing you needed to know about them is that they fit together and satisfy the technical assumptions. But in reality, trying to do this analysis for real clinical problems, the choice of data for the target population and the choice of the trials that go into the collection is a major design decision. And in many cases, is not one in which we have full control as investigators. For example, when we use existing data for the target population, or when we rely on existing trials that we didn't have a hand in designing, our ability to fit them together may be more limited than we would like. So the question is how to think about that problem. And of course, I'm being inspired by my many colleagues in the causal lab, Miguel in particular, who advocates for the target trial idea for designing observational studies. And I think one idea for principled thinking about these design decisions is to think about an ideal study that would address your research question. In my case, in the causal case that we looked at together, the ideal study tends to be some kind of survey experiment, a study in which you know the target population, you survey members from it, maybe using formal sampling, and then you randomize those individuals. And so many of these are done, but not commonly in medicine. And so my idea here is to use that survey experiment as an ideal study, write down a protocol for how you would do it, all the design elements, which would be more than the design elements for a target trial, since you'd have to capture the survey piece, and then take the available data sources and compare against that ideal study, and be able to make a credible scientific argument on why the data sources you chose are the best available for emulating that ideal study. And so this involves similarity judgments. And my friends in philosophy tell me similarity is a very dangerous idea, because in the end, everything can be argued to be similar to anything else. I don't know, in a book I think I saw, a person can be argued to be similar to a crumpled piece of aluminum foil. If you look at the right, I feel philosophers are like that. But I think this is good from an epi standpoint because it's the part where the judgment will always remain. You have to understand the data and how they're collected and understand the problem and what would be an answer, a reasonable answer to it, to pass this similarity judgment. So to me, it's a good thing that they are subjective in a way. Now, another problem with sampling that we have been pressed to no end to try to answer by grant review panels, so I'll take any ideas you may have on this, is how many observations you need from R0. I mean, in grant review panels, they'll usually press you to do a power calculation, and we are resisting because the data is already there, so the meaning of power is not really clear. It's not like we can collect more data to attain greater power. In any case, as a heuristic, I'll say, if you're thinking about pursuing these analyses, a lot of the precision is driven by the trial data. So if you have a choice of, if you have money only for one extra data point, almost always that money is better spent on doing a slightly larger trial. The idea being that after some sample size, the impact of our zero observations on your precision plateaus because they don't contain any outcome information. Essentially, you just need to characterize the X distribution in their zeros, the covariate distribution. But once you have a solid estimate of that, money is better invested in doing a larger trial. And then we have some work in this setting where you design the sampling and you design the entire study, and we try to do this with cluster trials because you have more control on which cluster will actually participate in your study. Humans are a little more finicky. And so that's all I'll say here. But it seems to me this is a huge area for future research. What is the optimal design of these to support this analysis, especially if you have some design control over both the trial design and the target population sampling design. This one is too esoteric, so I'll skip. And just to summarize, what I think we did today is we have some framework for combining information over multiple sources to learn about parameters in a target population. And I tried to use a narrow, simple, work with me kind of example to highlight the elements of the framework. And that was causally interpretable meta-analysis. Contrary to popular belief, I hope I have at least in part argued that this combining of information is not just about data and standardization. It's a truly full causal problem that requires understanding of the assumptions and how they relate to the data that you have available. Even in our simple example, quite a bit of substantive knowledge is needed to argue in favor of these assumptions being at least approximately true. And then I didn't have all the time in the world to go into design, but these issues seem to me at least on par with issues of identification and estimation, and as such, fertile grounds for further research.